We're going to get underway. So welcome everybody, and thank you so much for coming out on a cold Melbourne blustery night to play with astronomy, listen to astronomy and join us for a lot of fun. My name is Professor Virginia Kilborn and I'm Chief Scientist here at Swinburne and also a radio astronomer, and it's an absolute delight to be chairing this panel session today. Before we get started, I'd like to respectfully acknowledge the traditional owners of the lands on where we are, the Wurundjeri people of the Kulin Nation, and pay my respects to elders past, present and emerging, and extend that welcome to any Aboriginal and Torres Strait Islanders that we might have in the audience today. So today we're going to travel through the universe. I'm just going to say that. We're going to start from Earth and work our way out. We're going to hear from these wonderful panellists who I'll get to introduce themselves a little bit later. There'll be some time for audience interaction. We do have prizes, just saying, so, you know, think about the questions that you want to ask. There'll be some time for questions later. And I'm going to say, so you can trick the panellists, but that's mean, so just think of things that you actually want to know. And then we'll end the event in about an hour. So let's get underway. I'm just going to sit down here and pretend I'm introducing myself. Okay, so what I'm going to do is get our panellists to introduce themselves and then tell me a little bit about your research area. And our theme for tonight is decoding the universe. Or decoding the universe. I'm not sure about the emphasis on that. So could you tell me what decoding the universe means to you? So your name, research area, and decoding the universe. How are you decoding the universe? Thanks.
Right. Good evening, everyone. I'm Dr. Rebecca Allen. The picture should help you up there. I'm the co-director of Swinburne Space Technology and Industry Institute. I also have a PhD in astrophysics, where I study the evolution of galaxies going all the way back to when the universe was roughly a few billion years old. Of course, James Webb has now come through and just swept all that away, but that's all right, because that means there's more research to be done. My area of research. So if you couldn't tell by all the words that I jammed into my title, I basically just love all things space. So from looking out into space and trying to understand the evolution of those very first galaxies and how they grow and evolve over time to the galaxies we see in our nearby universe, but then also thinking about how on Earth we use space every day, and actually thinking about how we can use space to help us. And how we can actually send things into space, like experiments that go to the International Space Station. So what I help do is to actually translate a lot of the different areas of research we do so that we can grow our own space industry in Australia. Because as you guys might know, just a few years ago, we started, Australia now has its own space agency. We're now building our first lunar rover. And I'm actually helping some of the researchers at Swinburne who are designing really important technology for that. Quick question, does anybody know the name of Australia's first rover? Any guesses? It's really original. Skippy. Rover. Yes, I heard the size. I didn't name it. Okay, so decoding the universe. What does that mean to me? Well, as a scientist, actually one of my favorite things, especially about doing a PhD, is you start off thinking, I'm going to answer this question, I'm going to figure this galaxy evolution stuff out. And then not only do you realize that you don't answer that question, but actually many, many more questions just start popping up. So to me, decoding the universe means that we're thinking about some of the big fundamental questions, but then we start to realize how beautiful and complex our universe really is. And that's amazing because that makes us, like James Webb coming after Hubble, completely change what we think about things like, you know, early galaxy evolution. So for me, decoding means that we're actually learning more and changing some of our first ideas. Yeah.
Thanks so much, Rebecca. That's amazing. Kirsten.
Hello, I'm Dr. Kirsten Banks, or you may know me on social media as Astro Kirsten. I am a astrophysicist and lecturer is my job title here at Swinburne, but it goes beyond just teaching in a classroom like this. I do a lot of social media, and the way that I decode the universe is decoding what the scientists say to then let everyone else understand what's going on in the world of science as well. So that's what I enjoy doing. But within my research, I also do a little bit of galaxy evolution. I've dabbled in galaxy evolution and into galactic archaeology as well, which we'll talk about more later. Yeah, we all want to know what that means. Bailee.
Hello, everyone. I'm not yet Dr. Bailee Wolfe. I'm a PhD student here at Swinburne, and I actually study, I'm also a radio astronomer, like Virginia said, but I specifically work with telescopes that are spread across continents. So a lot of times we'll say we work with telescopes the size of continents. Maybe some of you know that there was a picture taken of a black hole for the first time. That was using the Event Horizon Telescope, which is an example of the type of work that we do, but for different subject matter. Hopefully we'll get to talk more about it later. To me, decoding the universe really means trying to break down a really complicated, difficult problem into something small and manageable. So I really love trying to find big science questions that people have, issues that they're having with observations, things like that, and then breaking it into small pieces that you can actually work on, like as a person, as a research group, things like that. Like there are big, scary questions, but it is manageable to kind of like break it down.
Fantastic, thank you. Welcome, and Sparrow.
Hello, I'm Sparrow Roch. I'm also a PhD student here. I also do radio astronomy, and I get to think about a very cool type of star called the pulsar that is very tiny and spins very quickly. And when it's spinning, it's also yelling a lot of light at us, and I get to listen to the light that it yells at us. And we can learn from those signals that we observe. I get to think a lot about the maths process that we do and the writing code process that we do for studying about these astrophysical signals. So in that, I also think about decoding, kind of as we all said, decoding to me is just the process of learning. So when we have these signals that we receive from space or when we're looking out into space, decoding is really just making sense of something that we don't understand yet, which is what we're all here to do. So I think the process is, decoding is doing science.
I love that. Decoding is doing science. So, well, we've got a great panel for that. So we're now going to take a journey through the universe, and we're going to start with our very own solar system and have a bit of discussion about what's in our solar system and what do we know about it and what do we know from different ways of observing the solar system. First of all, I'd like to ask the audience, who knows what's the closest planet to the sun? Anybody? Yeah?
Mercury.
Mercury. Oh, what about the second planet? Do you know that one?
Venus.
Venus. And any others? Do you know any others? Anybody know any others? What comes after Venus?
Earth.
Earth? Then? Do you know what's after Earth? It's red. Is it chocolate? Yes, that's it. Mars. Okay, now we're going to get a bit further out. So those four planets are all rocky planets. So we can fly probes to them, we can land on them. Mercury's pretty hot on one side of it because it's near the sun and cold on the other side because it doesn't have an atmosphere. But you've probably all seen rovers on Mars and so on. But what about the next planets in the solar system that are further out than Mars? They're called the gas giants. Does anybody know what that is, yeah?
Jupiter.
Jupiter! Yeah. The best planet? Yeah, that's right. I know. What comes after Jupiter? Yeah?
Saturn.
Yeah. And what's amazing about Saturn? You see it?
Its rings.
Yeah, seen the rings. Has anyone seen the rings of Saturn through a telescope? Yes, now, if you haven't, you need to take the opportunity to see it because it looks exactly like the images. It's amazing. I mean, the first time I saw it I was probably 20 and I was just like, oh my gosh, it looks like a postcard. So it really looks like that. Saturn, what comes after Saturn? Yeah?
Uranus.
Yes, and? Neptune, okay. And then, yeah, well done. High five, everybody.
No more planets after that.
Okay, tell us about the other planets. What are the other planets that come after that?
Well, they are dwarf planets.
Okay.
Yes.
But of course, we have our beautiful Pluto, which loves us back, so it has a nice little heart on its surface.
Beautiful. So we do have dwarf planets. And what else is in the solar system? So we've got planets, dwarf planets,
Stars.
stars. One star in our solar system?
Yeah.
The sun. Yep.
Sun. Yeah.
Yep. What else? Asteroids. Anything else?
Oort cloud.
Moons.
Oort cloud.
Oort cloud. Comets. People.
Nobody said aliens.
I was going to say aliens. Okay. All right. So we've got a good view of the solar system. So when you go outside and you look at the sky, you can actually see some of these objects during the day, like the moon and the sun during the day. And the moon isn't a day object. I'm just saying you can see it through the day and during the night sometimes. But also you can see the planets. So what we're going to talk about is what we can see with the planets and what we know about the solar system. So Kirsten, I was wondering, I want to start with you, and in particular, I know you've done a lot of work on Aboriginal and Torres Strait Islander astronomy, and Australian First Nations peoples were the first astronomers, 65,000 years of knowledge. What can you tell us from that perspective around the solar system?
I love this so much. I've actually published a paper with Professor Dwayne Hammaker about the role of planets in Aboriginal traditions. When we look up at the night sky and we see the planets, there's a common theme throughout many cultures across the world that the planets are the wanderers. They are the moving stars because they change position in the night sky from night to night because they're much closer to us when we see them move around the solar system. And in many different indigenous cultures, for example, up in Yolngu country, up in the Northern Territory, they would see the planets as the wanderers. But beyond that as well, they noticed that all the planets appeared to be in a line across the sky. And because of that line, that's because of how our solar system was formed and the geometry, the placement of all the planets in our solar system. They're able to use that as navigation. And as a navigation tool throughout the night. So there's some really awesome science within that. But there's a really fun one as well that I want to finish on about a Gamilaroi tradition which talks about Venus. Venus, in their traditions, is an old man who laughs at his own jokes. And the perspective of this planet laughing at its own jokes is when Venus is low in the sky. Its light is going through a lot of the atmosphere and it twinkles a little bit. Planets generally don't twinkle, but when Venus is low in the sky, it does. And that twinkling is the representation of the old man laughing at his jokes.
So that's in every culture then. Thank you, that is amazing perspective. And Sparrow, I was just wondering from the Native American point of view, do you have a different point of view on planets and what they look like in the night sky?
Sure. Well, I think first I want to just put out there's no single Native American view because, as in Australia, there's so many different tribes and nations that exist in Native America and still today. But I think they do have these sort of common themes, kind of like Kirsten said, that when we see the planets, they are like the wanderers that might have like, oh, this is an indication that we're doing some sort of ceremony is happening or some type of celebration. They were often regarded as like messengers that had an important like life lesson or something that you might need to know. It's interesting you mentioned about Venus being the old man because I think I've heard more about Venus being like a wise woman who guards the evening or the morning depending on the time of day. So you might think, oh, I have to do this really important thing while this wise woman is watching out for me. So it's a little bit different that way. But I think maybe a common theme in a Native American perspective is that we don't view the sky as this thing that's just so far way out there separate from us. It's part of our Earth sky system and actually like a living member of our family. So there's a bit of respect and I like to think reciprocity when we learn and study about the sky.
Oh, that's amazing. Thank you so much. So Rebecca, I'm going to ask you, you've talked about space exploration and firstly I'd just like to know, like we know a lot about the planets as in what they're composed of and so on. What are your thoughts on space missions and what we've learned from space missions about the planets?
Well, I think it's been incredible to see, Mars is, the planet that's most inhabited by robots. We've been able to send so many missions there. And I love the kind of comparison of like Goldilocks and the Three Bears, where you have Venus and Earth and Mars. And why do you have planets where, Venus and Earth, so similar in size, but so different, and just understanding, the fact that time is so important because, long ago, Venus may not have been that different from Earth, and Mars might have had oceans, but over time, we know that really changed. But having the rovers on Mars has shown us, evidence that there was actually not just water, but there was flowing water. I actually think, though, sorry to shade the planets, but I think probably one of the coolest things that we learned is that planets are nice, but the moons, especially the Jovian moons and like Enceladus around Saturn, they might have vast oceans under their surfaces. And we know this because of an instrument called a magnetometer. And it's because these instruments, they go out and they can actually tell, they can detect from the magnetic fields that there's probably vast bodies of water in the moons that are around Saturn and Jupiter that are way far away from the sun. So to me, my brain is like, wow, how can there be more water locked up in a moon way far away, and probably better potential for life than on any of the planets that are out there? And so it just shows you how, with the advances of technology and what we're able to detect, and like Sparrow was saying, like using the math and decoding these signals, that we've found these hidden treasures around the moons. So I can't wait for JUICE and the other mission. Which one is it?
Oh, Europa Clipper.
Thank you, Europa Clipper. I can't wait to see what results that they show us about those moons. So yeah, that's probably the one I'm the most excited about.
Yeah, it's so fantastic to see these still happening. I understand, or I actually know, and am part of, that you are running a program for kids to send experiments to space and to the International Space Station. So what would make that interesting? What happens in space that we would want to send an experiment specifically out into, say, onto the space station? And what have you learned?
Well, first of all, Virginia helped start that program, so awesome, thank you, Virginia. We are now actually getting ready, next year we'll be sending our 7th and 8th payloads to the International Space Station. And the International Space Station is a laboratory which orbits Earth at about 300 kilometers away, and it's so important because for over 20 years, astronauts have been undertaking science there. And it's because we don't know. We just don't know about the perils of space. And if we want to send humans to the moon, we have to have a place to be able to kind of, like our jump-off point. So that laboratory has been really important. But what we've realized, especially in Australia, is how do we get you all, ready to lead these space missions? Well, we have to give you the experience of actually leading your own mission. So you guys get to decide the science. What do you think is an important question? And a lot of the times our students are like, well, what's going to happen to the astronauts' teeth? What are they going to eat? What about their tummies? And these are the same exact questions that the NASA astronauts are like, yeah, cool, we also, want our tummies to be okay, when we're in space. So we've gotten to, work with high school students and our own undergraduate students to design these missions. And so what that means is that the first plants grown in space by Australians, the first yogurt cultured in space by Australians, and the first fungi sent to space by Australians was all student-led teams, right? So it's not just like the super, doctors doing this. This is something where we're giving, the next generation opportunities because you guys are the ones that are going to go out and solve these problems. When we think about going not just to the moon, but beyond that, there are questions we haven't even thought of yet in those challenges. So we think it's so important to do that and to get to take part in these missions.
So fantastic to have that opportunity, and also just to see what happens when you send things into microgravity.
Yeah, sorry, I was just going to say too, we can talk more about this after, and there are prizes, by the way, and 2 of those prizes include some of the seeds that we've sent to space, and you get to compare them with Earth seeds. But it turns out even something as simple as growing a plant, when you take away gravity, it gets weird real fast.
I remember seeing a video of bubbles in space, and we could just watch that all day, really, it's weird. Okay, well, I think we've done the solar system. We're going to move to stars and the galaxy. And does anyone know what our own galaxy is called? Yeah?
Milky Way.
Milky Way, yeah. Who's seen the Milky Way? Everybody? Yeah, you probably... Yeah, you want to leave Melbourne to see it properly. Not forever, just to see the Milky Way. So, the Milky Way has, I'm going to say 1 billion stars. Is that right?
400 million?
400 million? Okay. Well, that's within...
A lot.
Yeah. Let's say 500 million or plus or minus a little bit of stars. Anyway, it's got a lot of stars. You can see about 6,000 with your naked eye if you're out in a really dark area. And all of these stars, they're different sizes. There's really big, bright ones, and they burn up fast, and then they die in things like supernovas and planetary nebula, and smaller stars that sometimes just go into white dwarfs. And we're going to hear about the end point of stars called pulsars, which are neutron stars. And I'm going to turn to Bailee to tell us, what am I talking about?
Sure. So, like you said, pulsars are one of the multiple possible endpoints of stars. So stars have a lot of different shapes and sizes and colors, right? They're not all like our sun, which is kind of like a nice middle ground star. And they age just like people, and sometimes at the end of their lives, they do something really interesting. If anyone can tell me what happens at the end of a star's life, I would be super excited. Oh, I saw a hand. Yeah?
I think they explode.
Yeah, so stars explode, and they explode in things called supernova. So some types of stars at the end of their life, they kind of run out of energy, and then they'll explode. And some of them leave behind really interesting objects that we're interested in, what we do a lot of research on, like black holes, for example, or what Sparrow and I both work on, pulsars. So these are leftover stars, dead stars, that are super, super, super dense. Think like hundreds of times the mass of our sun, but about as far across as the city of Melbourne. So they're really dense, really small stars, and some of them spin really rapidly. And because of all of this mass concentrated in this really small place, they end up kind of like shooting off beams of radiation in either direction. So you might hear them referred to as like lighthouses, because they, like Sparrow mentioned, they spin, which is fun. And yeah, this is like one of the biggest things that we can do with these is test fundamental physics and a lot of really big science questions, because they're super different than anything we have on Earth. I do this specifically in a very roundabout way, because like I said, I like taking a big problem and breaking it down into very doable pieces. And so we want to study pulsars. People like Sparrow do a lot of really good work with timing the pulses of a pulsar as they spin around. And I use these very large radio arrays to try to measure the distance to these pulsars. So I want everyone to do something real quick to try to explain how we do this. You can hold out your thumb in front of you about arm's length, and then blink your eyes back and forth. You should see that your thumb looks like it's moving back and forth. And if you move your hand closer, it changes how far apart it looks like it's moving. So we use something like that to try to figure out how far away these pulsars are from us. So we're using these really big radio telescopes, and on the sky, when we observe them long enough, we can tell the change in their position to something called micro-arc-second precision, which for everyone, I learned this actually this week, a good example to compare, is if we put a coin, just a standard coin, on the surface of the moon and moved it back and forth, that's the difference in being able to tell like a micro-arc-second on the sky. So these things are super far away, and we can get really accurate distance measurements and really accurate information that then people like Sparrow and other really cool researchers can use to better understand physics and pulsars and star life cycles.
Thank you so much. That's so interesting, and I love that experiment that we all did. Hopefully everyone came along for that ride. And Sparrow, so you were telling me you use radio telescopes to understand pulsars and potentially gravitational waves. Is that right? And could you tell us a bit about what that means and how you do it?
Sure. In lieu of having us all stand up and spin around with our arms out, we're just going to have everyone try and imagine a lighthouse, but the lighthouse is in space. But the lighthouse is also rotating at a very regular rate. So every time its beam of light would pass over us, we could expect it to come at regular intervals. We do the same thing on a real scale with pulsars, which are these stars that sort of behave in a similar way. Each time their signal passes over us, it happens at a very expected time, or at least we hope so. The science behind it is if there's any difference between when we expect that signal to get to us versus when it actually does get to us, then we can start decoding why did that happen. The exciting, I think, biased reason that might have happened is maybe that signal was traveling through something in space, or maybe the space itself changed somehow. Traveling on a straight line, you can go a farther distance, but if you're traveling on a wiggle, it takes a little bit longer. So maybe the signal was on a wiggle, and maybe that wiggle was caused by gravitational waves. So that's kind of the basic idea of how we use pulsars to do that science.
It's mind-bending as well as universe-bending. So yeah, thank you for telling us about that. I'm going to move to Kirsten now, and you mentioned galactic archaeology, and that's in the Milky Way. And what is archaeology of the Milky Way?
Right, so when we say archaeology or an archaeologist, what do you imagine?
Rocks.
Rocks, exactly. Rocks, you're digging through stuff to look at really old stuff to figure out what old people did with that stuff, with communities and whatnot. Same basis, but with the galaxy. So instead of artifacts, we're looking at stars and how old they are, where they existed when they were born, what they're made of, so how they came together and what parts of the universe came together to create those stars. And we can rewind time to the time and place of the birth of these stars to figure out what the history of the galaxy was like at the time and place of that star's birth. So it's kind of like putting together a photo book of the Milky Way galaxy, trying to understand its 13.4 billion year long history. It's a big photo book. Lots of gaps in the photo book as well. But that's kind of what galactic archaeology is. It's looking at the history of the Milky Way galaxy, basically being Indiana Jones, but for space.
What an image.
Also, clearly that reference went way over the kids' heads. It's a great movie. Indiana Jones, check it out.
It's like being Dora the Explorer in space.
So what did you find? I mean, did you find ancient civilizations? No.
No ancient civilizations, unfortunately, not yet. Otherwise, I'd be a much more famous scientist if I did. No. So what we find with the Milky Way galaxy is some really interesting things. In that the Milky Way is a bit of a hungry hippo when it comes to a galaxy. It has consumed a lot of its galactic neighbors. And we can see that by looking out into the space around the Milky Way, and we can see streams of stars left behind from old galaxies, smaller galaxies, some slightly bigger, that have been ripped apart as the Milky Way is gobbling them up to increase its size.
Oh.
Yeah. I did this for my...
I know this, but when you say that, it just seems so dramatic.
I tried to call my thesis a tale of galactic cannibalism, but my supervisor said no. So, we've been talking about our own galaxy, the Milky Way, but there's billions, half a billion, hundreds of billions of galaxies, hundreds of billions of galaxies in the universe. And we can look at galaxies with different instruments, and we're going to talk about instruments in a second.
But Rebecca, I know you've done a bit of work on galaxies in the early universe, so galaxies that are very, very far away from us, but we also say that's the early universe. So could you explain why is it that when we see something that's a long way from us, that we're looking back in time? And then what did you find out about galaxies that are different to galaxies that are nearby the Milky Way?
So our wonderful universe is not a static one. It has, since it was born, it has been growing and expanding. So just like we were talking about earlier, with the light coming from a pulsar, it is embedded in the space and time that it's in. And so if you're in the back of the room and you are shining a light at me, that light's it's not going to be as bright as if you're closer to me. And it's also because that light gets stretched with the expansion of the universe. And so that's a phenomenon called cosmological redshifting. And that's what actually allows us to, in a way, really look back in time, because the light from the very furthest parts, it takes so long to get to us that its light gets shifted. And so we can tell that that light is very, very old. And so that helps us understand, well, we were talking about individual stars and systems in our galaxy, but that light is coming from galaxies that existed, we're seeing it as it was billions of years ago. So before they became hungry hippos, what did they look like? Were they smaller? Are there different kinds? Did they all look the same? And so we need to look back at that early starlight to be able to try to understand the different populations of stars and galaxies, and then how did they grow over time? And so that's what's really important about going back and looking back. But just like we're talking about radio astronomy, there's all different types of light that we can look at. So to see the most distant galaxies, this is why James Webb is so important, is it's looking really at the reddest light. So what we call the infrared spectrum. And that's because that light has just been stretched so far. So when you see the pictures of the James Webb and it's like, oh, this red smudge is actually the oldest galaxy ever detected. That's a red smudge. And that's because, that light is just so far away. And so it's incredible to see these things just kind of popping out. But it's a numbers game. So this is the other part of it too, is just like for pulsars and stars in our galaxy, we need to see a lot of them to really understand the patterns.
Well, thanks very much for that really clear explanation. So the final question I sort of have on galaxies is sort of going back to this idea of First Nations people in Australia and Native American ideas of what the galaxy looks like from Australia or from the northern part of the sky. So we know that the Milky Way is seen best from Australia, but you can also see it in the northern sky. And I was really interested then to think about what are the different phenomena that you see in the different parts of the globe, and how has that affected the way that there's an understanding of the night sky. Would you like to comment on that?
Yeah, sure. I'll share with everyone a really cool thing that I learnt about the Milky Way from my Wiradjuri perspective. And it's that the perspective we see the Milky Way as is of a series of waterholes. So kind of similar to the Milky Way being a stream of milk when it comes to the Greek interpretation of ancient Greek interpretations. In Wiradjuri astronomy, we see it as a series of waterholes. But here's the really cool part. I can guarantee you all, potentially all, know the word that we call the Milky Way in Wiradjuri. I'm going to say it in Wiradjuri language, but think if you recognise the sound of this word. Billabong. Billabong. Yeah. That's where that word comes from. So a traditional Wiradjuri word for the Milky Way galaxy just by happenstance because it has continued through into the English language. And it is also a clothing brand, I think, still. I'm not sure if there's still Billabong stores out there. But yeah, so that's our perspective of the Milky Way. But we can also see other phenomena like dark constellations. We have a dark emu we call Gorman in Wiradjuri astronomy, and its position in the night sky indicates to us when is the right time to go looking for emu eggs. So it's also a seasonal menu of sorts. But I would love to hear more about Native American interpretations of the Milky Way.
Sure, I think it's the same for a lot of Native American cultures that also use it as this seasonal marker or other type of calendar event. Instead of being a billabong, though, I think the most common lore that I've heard about seeing the Milky Way is sometimes we talk about looking up at the sky as we're looking into the heavens, and the dust of the Milky Way that you can see in a very dark sky is commonly referred to as the path of souls. So it's almost like this bridge between us here on Earth and a connection to spirits who have maybe passed on. So if we can see the Milky Way, we might think, okay, all of the souls that are ready to leave are going to rest. Or it might be a time of the spirits that need to talk to us are coming back. So it's a really important time that way, I think.
Oh, that's very powerful. Yeah, thanks so much for sharing that. Yeah.
Well, that's been a really fascinating discussion, and I feel like we've have a really nice understanding from different perspectives of what's really nearby us, but also what's at the very edges of the universe. And so I want to shift the focus a little bit about being a scientist, being an astronomer. What's it like, and why are you here? Why are you doing astronomy? Not the big question, why are we here, but why are you personally here? And really, Kirsten, I might just start with you and just ask, what was your own light bulb moment? How did you become an astronomer? What made you come down this path?
Yeah, for me, my spark began in about year 9 or year 10 when my science teachers took my entire year group on an excursion to go see a documentary about the Hubble Space Telescope. And I remember sitting in the IMAX theatre in Sydney with the 3D glasses looking off my face because they don't fit anyone, watching this scene where it showed a virtual fly-through of the Orion Nebula. And I was just enthralled with how much we could learn about distant objects. Like, this thing is 1,300 light years away, which is close compared to the galaxies that you study. But it was amazing to me of how much we could learn about this object, know that there are stars being born there, know that the stars are made up of these chemicals and elements just by looking at the light that it emits, and it doesn't emit as well. So literally decoding what I like to call the barcode of these distant objects. It was amazing, and from that point I'm like, yep, that's what I want to do, and now I do it, which is great.
What a story. It's a real story of success, so well done. That's really fantastic. So Bailee, then I'm going to ask you, what's it like being a scientist? What do you do on a day-to-day basis, and what do you do outside personally? You don't have to tell us a lot, but how do you balance being a scientist with all the other things that humans like to do as well?
Yeah, that's a really great question. I think when a lot of people think of scientists, you might get this kind of like unique ideal version. It's like, someone bent over a computer late at night doing work, or like kind of off on their own and just constantly thinking of big ideas and writing out equations. But it's not always like that. I'm sure some people have their moments. Especially for me, I'm not a theorist. I do observational astronomy, so I work with telescopes and things like that. And that takes a lot of cooperation with other people. So actually a lot of my work on a day-to-day is figuring out how to schedule observations. If I want to look at a certain object, we're trying to look at pulsars, and then I have to talk to people around the world to make these observations happen. So I'm working with people in North America and Europe, and that takes a lot more people and communication skills than maybe you would, grant the average, media scientist. So a lot of my time spent talking to people. We spend a lot of time discussing ideas just as a department, as groups. A lot of us probably spend a lot of time in meetings. But I also find it really important to know that scientists are people outside of their work too. I have a lot of interests as a person, and I try to bring those things into my work as much as I can, and also try to maintain some sort of balance, especially when we're dealing with really big questions like the universe and scales that are hard to think about. Sometimes it's good to take a step back and, at some observatories, things like that I've worked with, there's groups of people that all play instruments, so then they're in little astronomer bands. And so you can take a break from thinking about the the end of the universe to go and play music for a little bit and just kind of forget things. So yeah, it's really important to find a balance and also to know that scientists really have to be good communicators, and a lot of your job is working with other people to make good things happen.
Thank you, very wise words there. So Rebecca, I was wondering if you could tell us, for anybody who's in the audience of any age, what do you need to do to become an astronomer? What sort of skills, what's the mindset, where do you go and how do you do it?
So first of all, I'll say, obviously everybody's path into science and astronomy is different. I encourage you guys to come up to us after. We've all got very different journeys. But really, if you want to become a scientist, the thing is, you got to go to university, and then you usually do a postgraduate degree. But that initial stage of getting into it, so as I mentioned before, we like to give students hands-on opportunities. We also have our Space Innovation Challenge, and I think that's really important because that's for secondary students who want to come and you just want to try out all the science. You want to learn about gravitational waves and pulsars and galaxies and astronauts and rovers. So we have that kind of activities. In Swinburne now, we're so excited because we've had an astronomy minor for a while, but now we're going to have an astronomy and astrophysics major. So when you're in university, you usually take about 4 years to do an undergraduate program, and so now we'll have a whole program. You don't have to share it with any other science unless you want to do a double degree, and that's fine. But you can focus totally on astronomy and astrophysics. We also have a space technology co-major. So if you want to, dabble in physics and astronomy, but then also learn more about working in space industry, that's what university really teaches you. It teaches you the fundamentals and gives you a bit of a taste of things like industry and research. And then you go on to do a postgraduate degree where you become the world expert at that thing. And that's what I try to encourage people, especially still doing their PhD. They're like, oh, I don't know. And I'm like, nobody on this planet knows more about those pulsars than you do. Nobody. And that's so cool to know, and also terrifying, because you're like, well, what if somebody's gonna call me out on not knowing the precision of this thing? And nobody is, because you're the expert. And then you can also work in industry as well and get experience, with missions and helping build satellites and things like that.
So many options. That's fantastic. Thanks, Rebecca. So I hope everybody's thinking of questions to ask. Well, I'm going to ask a couple of big picture questions from the panel, and then we're going to go to the questions from the audience. So the first question is for Sparrow, and I'm wondering, and this is a big question, what do you think the universe will reveal to us in the next 20 years that will completely change our understanding of reality?
There are so many things to learn from the universe, and I will speak on one of those things that I am hoping for. Something I think about often is we have right now two main theories or idea of how physics and science work. We have quantum mechanics, which is a science thinking about really tiny little things. And then we have general relativity, which is thinking about really huge, big old guys. And those two theories have never been incorrect in their own areas, but they kind of contradict each other. So they can't both be correct at the same time, but they've both never been wrong yet. So we're still trying to find a way to have those two theories get along with each other, and I'm hoping that, maybe this is ambitious, but I hope that pulsar astronomy can help with the puzzle pieces of that. But I think that all of us are contributing to putting all of those pieces together and making sense of the universe as a whole. And also, it would be cool if aliens are real.
Well, smallest to biggest to aliens, and I'm going to ask about aliens. I mean, it wouldn't be an astronomy panel. It would be an astronomy panel if you don't ask about aliens, but it's not going to be this astronomy panel because I am going to ask everybody, if humans make contact with extraterrestrial life in our lifetimes, what's the first thing you want to know? Rebecca?
Oh, I have to go first. Okay.
You didn't read the questions beforehand,
No, I
so
didn't.
now you're saying sorry.
This This is an important lesson to all you students. Always read the instructions and the questions before the test. The first thing actually I would ask them is, when they look out in space, do they get the sense of they feel like they're alone, or do they feel like they are actually connected through everything? Because one thing we know, especially about physics, is that we are kind of, tied together through like quantum mechanics and everything. And so for them, is it this great expanse of nothingness, or are they just excited to find other life forms out there? Maybe not the most intelligent, but still. Or is it like we're all connected, it's cool anyway?
Great question. Kirsten.
I think I would like to ask them if their physics is the same as our physics, or their interpretation of physics. Because if it is truly universal, that would be huge. If it's not, what? So I'd love to know that.
Yeah, I want to know that too. Bailee.
I feel like my answer is a little bit similar to Kirsten's, but I would want to know how they view time and space, especially depending on where they're at, right? Like in our universe. Like how is that different for them? I don't know. I just think that's interesting.
Fantastic. And Sparrow?
I would ask them, what's your life story? Because I think you can learn a lot about asking that question, because what people think is important to them is usually that's included in their answer. And so I think that's maybe a little more anthropological than astrophysical question, but I think it's quite interesting to me to think do they have a favorite music? Do they have music? Do they have a favorite flavor? Do they even eat things? I think that helps keep a more relatable connection, and we could learn a lot from it.
I love how you guys are all so deep in this answer. I was thinking, what's your favourite snack? Do you have cars? Anyway, thank you so much. The very final word from all of you, just one sentence. So these guys have listened to you talk about everything from quantum to gravitational waves, stars, dead stars, growing stars, galaxies. How do you find out more about this if you're interested?
Can we start on that side this time?
What would you recommend? What are good resources that you would recommend?
I think collaboration is the spirit of science, and there is so much to learn from the people around you. I think maybe I'm the least qualified to talk about do this program or do that program, but I am here to be a cheerleader for learning from the knowledge of others who are willing to discuss these sort of things. And it maybe sounds cliche, but follow your interests. I did that, and now I get to be here thinking about astronomy every day.
Wonderful, thank you so much. Bailee?
Yeah, I mean, a little bit similar to Sparrow, but I think the biggest thing is don't hesitate to reach out to someone if you're interested in something. Like any of us are happy to answer questions after this or at any point. It can never be understated how much having a mentor or just a friend is in terms of learning more, even if you don't want to be in the field, if you're just curious or interested. Because a lot of us have things, like if we're doing astronomy and we're scientists, we also have things to learn from other people, from other perspectives. So those conversations are not one-sided. It's beneficial for everyone. And also in terms of programs, like Sparrow said, follow your interest. If there are things available to you, take advantage of every opportunity you can, because you never know where you might make connections, where you might find something that you just really love. So if you're curious about something, just give it a go.
Oh, that's wonderful. Thank you. Kirsten?
I will shamelessly plug my social media.
That's going to be my answer.
Mine or yours?
Both. No, you.
Oh.
You're going to be my answer, you and Sarah.
Yes, there's lots of really great science communicators on social media. Please follow me. But also for the under 16s in the room, I'm fully aware that the Australian government is banning you from social media soon. So you can still watch all of my content on YouTube without an account. And if you want to send me questions, I have a contact form on my website. So we can still have a conversation despite that happening. But yeah, Astro Kirsten on all your favorite platforms. Thanks, Rebecca.
Look, I would just say, following on the vein of this is just really to think about what makes you curious, what makes you wonder, and just in trusting yourself with that. For me, from a very early age, looking up at the night sky, it just always transfixed me, and I just stuck with that, and I followed it, and I read books, and I listened to amazing science communicators, and it continued to inspire me. And if you follow that, then you will never regret where it takes you. So whatever form you can find into it, it's really about following what you are the most interested in and passionate about.
Thanks so much. That's a beautiful way to end the discussion here, but it's not ending the session yet, because in the vein of asking questions, being curious, we've got some time for questions from the audience. So does anybody have any questions for our panel? Yes.
That's my
Great.
I'm not sure that this is a fair question, but nonetheless, probably it's directed at Kirsten Banks and at Sparrow. Now, do you know from the Aboriginal and from the sort of Red Indian tradition what their concept of time is? Westerners or our culture sees time in the Einsteinian theory of relativity. So how do the indigenous people see the concept of time?
That's a really deep question. And I fear that I don't have a solid answer for you, but it definitely is in some ways cyclical. In many different nations, if you happen to die before being initiated to a certain level, you essentially have an idea of being reborn back onto Earth, and so it's kind of cyclical in that sort of way. But yeah, that's definitely an interpretation, or trying to understand more interpretations of time across different cultures that really interests me. So I definitely identify within your question of hoping to find an answer to that as well.
I think from a Native American perspective, it might be a similar understanding of time, in the moments, like I'm thinking of the passage of time in this panel, or when do I get to eat a snack, or something like that. But maybe in a more cultural answer, I think it's a common practice to try and put more importance on remembering history. So for a lot of Native American cultures, even though an event may have happened hundreds or thousands of years ago, it still has the importance of something that happened more recently. So I think that's part of having that respect for those who have come before us, and having that sort of reciprocal relationship where remembering is also those people who have passed who are still benefiting us.
Wow, thank you for the question and those amazing answers. Thank you.
I have one quick one before I pass it to you. This one keeps whispering a question that she wants to ask. Is it okay if she asks one?
Yeah, of course.
Here you go.
She's going for that prize.
Yeah.
What is your favorite planet?
Jupiter, Jupiter, Jupiter. Next question.
And the reason you're wrong is Saturn. She's got rings, she's got the moons. I mean, come on. Yeah.
274 moons to be exact. Saturn is the moon queen.
But it doesn't have a spot. Doesn't have a big red spot.
No, but it does have a hexagon.
She doesn't.
It has a hexagon store on top of it, so that's pretty cool too.
What do you guys?
I disagree. My favorite planet is Uranus, and just because it also has rings, they're less impressive than Saturn's. That's fine, whatever. It rotates on its side, and that's so cool. So the Earth spins in a circle, and so Saturn does, and its rings go around. But Uranus goes like this, and that's so cool. It was probably knocked over something in the past, but that's awesome. So that's my favorite.
But it also smells like farts.
This might be a hot take. My favorite planet is Earth. There's so many neat things that happen here and so many interesting, exciting people who are also living here.
Plus we have Tim Tams.
And what's your favourite planet?
Saturn.
Okay. We have a probably a winner then. Never mind. Please go ahead.
I'd like to ask a question by way of example. If you look at the event horizon and what it achieved by the collection and aggregation of massive amounts of data to produce a picture, arguably by committee, you're all experts in your own individual fields. Do you imagine that there's some ultimate goal or focus or end point that you are trying to achieve by somehow assembling everything you've learnt into something amazing?
Who'd like to take that one? I say passing that on to somebody else.
Answer that one, Virginia.
Well, I can start. Look, I think what we're seeing in astronomy is that we are working together more across different regimes of astronomy. And so whereas stellar astronomy and planetary astronomy and galactic astronomy used to be very separate fields, and we have a radio astronomer looking at that particular galaxy and a optical astronomer looking at that star, we're actually now moving to the point where we're modelling planetary systems and stars at the same time, and stars within a galaxy, and so trying to put all of that together. We've got cosmological models, we run them in Swinburne on our supercomputer, where we're trying to put together galaxy formation, but at the moment we can only simulate galaxies at about 1 million stars resolution. So 1 point is about 1 million stars, and that's for the best sort of simulations that we have that can simulate many galaxies. So we're a long way from being able to simulate how a solar system forms within a galaxy and the galaxies within a cluster within the universe. We're a very, very long way from that. It is what we're working towards, but we had this talk, about relativity, and in some ways, exactly what a pulsar is doing here is interesting in itself. It tells us something about the universe, and does it exactly have something to do with how the earliest galaxies evolved? Maybe, but probably not. And so there is some separate elements of that, but yeah, eventually I guess we'd like to know that, but it's probably, I think we've got enough to get on with for our careers.
And it's like what Rebecca said at the beginning as well, is that every inquiry we make, every question we ask, spits out 5 more questions.
Yeah.
And I think to answer your question about what's the ultimate goal of scientists is to learn more about the universe around us, and it's really cool that we're able to do that every single day. And yet that goalpost keeps moving forward. There's always more and more to learn and more to uncover about the universe. And that's what I find really, really exciting about science.
Since I've got this, I might as well ask a question.
Well, we actually have a question up the back, and then can we come back? Is that okay? Just because...
I'm not leaving.
But you can remind me because you're right there. Yeah, it was... Sorry, the next person. Sorry. And then we'll come back, and then we'll go back.
We're just going to make Diana do stairs, eh?
It's okay, I had a lot to eat.
I was just wondering what was the most unexpected or absurd thing that you found in your research?
I have a fun one for that. It was a silly mistake there. I was, with the stars that I was studying in my PhD, I was trying to figure out how far away they were, and using the same technique that Bailee talked about with the parallax and the changing of the positions. I forgot a factor to the exponential of 0.2 and calculated that my stars were outside of the universe. Whoops. So that's probably one of the things that surprised me the most, and thankfully I've learned from my teachers to always sanity check the calculations you do, lest you publish results that break physics and then break your career. Probably that would be bad.
Oh, that's fine. Do you want to answer as well, please?
Yeah. This is a bit different. So I was working at NRAO in New Mexico, so at a radio astronomy observatory in the US. And we were summer students at the time, and they always very, very kindly give the summer students time on the telescope just to do something for fun. And it's really difficult to give a bunch of students just like free rein to do whatever you want on a huge telescope. But there had recently been a detection of something called like a transient event. So it's like happens and then it might disappear, you don't really know what it is. And it was like a binary system of two dead stars. And they saw it in not radio waves, so like an X-ray. And we decided that we would use most of our time to try to look at this thing that might not actually be there, just for fun. And so we were either going to see something really cool or we were going to see nothing. And then we got the data back, and like a day before, we took our observation, a day before we got the data, a group in South Africa with the Meerkat telescope messaged us and they were like, we looked, we didn't see anything. And so we were like, we're not going to see anything. We're summer students, we're busy. We just didn't even bother looking at it. And about a week later, someone came back and they were like, just look at it, just for fun, like just check. And we found something in the image, but it was a little bit to the side of where we thought the thing was supposed to be. And we found out that there was actually a typo in the original message that had said, we found this, X-ray binary, but this telescope at this place in the sky. And the other radio group also just looked in the slightly wrong place. And so when they looked back, like everyone actually saw the source. It was super cool and exciting, but a little typo made us think that there was nothing there and we were very sad for it. So that was fun.
Oh my gosh. Wow, and you found that as a summer student. That's amazing. We're pretty much out of time, but we've got two more questions and then we'll let you go. So we had one here and then or do you want to give your question to the kid behind you and then you can come up and ask us later?
I'll take the
What creates a hexagon storm?
What creates a hexagon storm on Saturn? That's what scientists are trying to figure out. But the best idea that we have at the moment is scientists, they put water into a container that could spin the water at two different speeds. So the inner part spins really, really fast and the outer part spins a little bit slower. And they found that when the difference between those speeds was a certain amount, a hexagon would form. They put dye into the water and it would create a hexagon that would stay like that for a long time and be stable. So we think it's because the wind speed of Saturn's gas is a certain speed here and a little bit slower here, making this hexagon happen.
Wow, wind speeds on Saturn, that's amazing.
I was going to say, is this something that she can try at home in her bathtub?
Ooh,
Because
yeah.
this is an experiment we could try at home somehow.
That sounds fun.
Yeah? Make some hexagons in the bathtub, what do you say? Yeah? Yeah?
We had one question there and then, sorry.
Hi, so I just wanted to know, what is our current understanding of, the origin of the universe? How did it all begin? Were the laws of physics different, or were they the same as it is today?
We don't have any time for any more questions. So sorry. Rebecca, looks like you would like to answer.
Well, this is actually a really easy answer. We don't know. No, and I say we collectively, this is one of the most interesting questions. And the reason is because we don't actually have the ability, right? Like I told you about this magnificent telescopes, we can see galaxies that existed right when the stars first turned on. We cannot see far enough back to see the beginning of the universe. So the best thing that we can do is to look around at the clues, like using cosmology, looking at where galaxies are around us today and things like the cosmic microwave background. And the best guess we have is that at some point there was, and we call it the Big Bang, but I mean, how it actually started, we don't know what was before it. Multiverses, sure. But, the idea is that at some point a switch turned on and then there was all of a sudden all of this energy and this expansion. And that is the most amazing thing is we know that much, but the actual mechanics of what happened at that first moment, we're still not totally sure. And we may never know. And I think that's actually cool, is that there's some questions that even with the biggest computers, Even when we combine relativity and quantum mechanics, we still may not know what happened in the very, very beginning.
Oh, that was a fantastic answer. Thank you so much, Rebecca. I'm sorry to everybody who we didn't get to the questions. We've still got a lot of hands up, but please come down and ask your questions. But before you do that, please join me in thanking our panel, Rebecca, Kirsten, Bailee, and if anybody is under the age of about 10 or so, 12, come down. We'll sort you out with some gifts.
Yeah.
Thank you so much, everybody.